questions in Discord chat, and then I just realized that the microphones, the phantom power for the microphone was off, so no one could hear me. Okay, well, I also just realized that there's a typo on the problem set and a pretty bad one. So we'll get into that. Are there any questions to begin with before we start? Um, my name is Scott, University of South Florida. This is Calculus 1. The last day of Calculus 1. Sad. And today we're going to be talking about initial value problems and the fundamental theorem of calculus, part 2, using that to solve them, as opposed to the antiderivative method, which we did before. So are there any also announcements? There is peer leading on Friday, but it is optional. I will post an announcement about that. I've been working on the discrete test. They're taking their test for today. I'll post an announcement about peer leading, when it is, where it is, obviously where it is. It's on Discord. The packet will be the test review that's already posted. I know I haven't updated the front page with all the links yet, but I haven't had a chance to yet. So I will get to that. Are there any other questions? Okay. Also the bootleg. I will have an assignment up for it sometime today. And remember that this evening's problem set session, or the test review for this evening, has been moved to 7 o'clock. It's no longer at 5. I know normally it's at Wednesday on 5, but the discrete guys are taking their tests, so I have to do that. Are there any other questions? Okay. If there aren't, I'm clipping. So if there aren't any more questions, I will go ahead and start going over the quiz. So the quiz today was a rather tough one. I admit that. It's got some of these problems that are... So, of course, the first one, the fundamental theorem of calculus. How do we feel now about stating that one 1 to 5? Everybody should have that as second nature. And as I promised, it was on every quiz since test 3. Except, of course, the survey one. All right, so we feel good about that. All right, let's talk about the second problem here. Quiz rubrics 15B. All right. So there are a couple things. You need to break this second problem up. You can't just do it as like this. The way you do these, it's asking for an antiderivative. So what do? Well, you do the antiderivative of the square root of x, which is really x to the 1/2, over x squared dx, plus the antiderivative of x to the 5 over 3 over x squared. All right, how do we feel about that 1 to 5? Just the breaking up of question 1, of part A. You have to break it up. Okay. I think there were a bunch on the web assigned like this. And then what you do, x to the 1/2, this is really the integral of x to the 3/2 negative, right? 1/2 minus 2. And this one is 5/3 minus 2. That's going to wind up being, if my math is correct, and it might not be. So this will be the 5/3. So this minus 2, this is, will give you a negative 1 over 3 dx. Okay. And then, so now we add 1 to our exponent. We deal with the exponent first. This is x to the negative 1 over 2. Okay. And then what would I need? I would need a negative 2 out in front to deal with this negative 1/2, because I want nothing in front. So I need to put a negative 2 in front of this in order to make it cancel when I bring this down, right? So when I bring down 1/2 and hit it with that, I'm going to wind up with a 1 in front, which is what I want. And the other one will be x to the 2/3, and then I need to multiply that by negative 3/2. And then I need to add my c. Okay. And then I need to check it. So the negative 1 here, the negative 1/2 here is going to hit that, and I'm going to wind up with x to the negative 3/2 minus x to the negative, here I wind up with negative 1/3 plus 0. And is that this? No, I messed up. Ah, there's my mistake. That should not be there. That would make that work. Right? Now when I take the derivative here, I wind up with the 1 to the 1/3. Now it matches. Okay? And that's why it's very important to check. Because if I didn't check, I would have missed that mistake. Okay, so let's see. Are there any questions about that? Could you do it without splitting the integral since you're just manipulating the fraction? You could set it up. You have. I mean, you are splitting up the thing. If what you're asking, if I understand correctly, is could I have just written this? Something like that. The answer there is yes. You could have just done that, but what you're doing afterward is technically splitting it up. But it's like the sum rule, right? Nobody cares. It's like the sum rule. You can skip it. Um, Technically, you did split it up, but when you did it, but it's like the sum rule. Okay, the next question, -3. How would it be -3/2? Because I made a mistake, which I caught because I took the derivative. And because I took the derivative of the thing I had, I figured out that I made a mistake about my sign. All right, so how do we feel about this one, 1 to 5? No, it's not negative. Ooh, I do need to change my answer. Right. I caught that mistake because of it right there. I caught that mistake that I didn't need the negative right there. Right? When I took the derivative of this thing, I caught my mistake. Okay. So this one's a little difficult. And it's mistakes like that that catch you. That's why it's important to do the derivative. Right? So now the question you're all wondering is, did I do that on purpose? Of course not. Is it okay if you turned x into a square root at the... Yes. So, yeah, any manipulation you want to do to that's fine afterward as long as it's correct. So you can do your algebra. All right, let's look at part B. Part B is tricky. There's 2 ways to do it. The best way is to use the fundamental theorem of calculus part 1. So this is just a limit problem. This is a limit problem. Now, if I direct sub on this, I wind up, this top goes to the integral from 0 to 0 of cosine of 2t dt. And what's that integral equal to? That thing on top is equal to 0. bottom goes to 0. So what I do is I do a little L'Hopital's rule. Now, the derivative of this on the top over the derivative on the bottom, which is just 1. And I need the limit sign, which I forgot. All right, the thing down here okay. Well, the derivative of AUC is simply f of x. And of course, the 1 goes the way. I mean, it's just there. All right. So that equals the limit as x goes to 0 of cosine of 2x. Well, that's easy to do. How do we feel about that? 1 to 5. Any questions? And that's a psychotic way to do it. Oh, I do need to put L'Hopital's rule. I also need to say that I did FTC here. Okay. Questions in the thing. Why would we go to AUC? Because I'm about to use this notation is better for, now you didn't have to do this, but this notation is usually better for FTC1, whereas this notation is usually better for FTC2. Because I was about to use FTC1, I changed notations. You didn't have to. You could have gone straight from this to this. Or you could have left this in here, d over dx of 0 to x cosine of 2t dt. Either one of those would have worked. I just get a little... whenever I'm about to use AUC, whenever I'm about to use FTC1, I generally prefer this notation. You could have done the other notation, and that's fine. All right. The other way I could have done it is I could have done it with FTC2 because this particular problem. Now, I can't always, right? Because I could have something that doesn't have a clean antiderivative. And this one has a little bit of a tricky antiderivative because you have to think about it. And technically what you're doing is U substitution, which is the first thing that you do kind of in Calc 2. But you can get away with this one because it's a simple U substitution. And you see it as soon as you take the derivative. So what I need to take... What I want to do is I want to evaluate 0 to x of cosine of 2t. All right, so I'm going to let f of x equal cosine of 2x. Now, what's my g? This makes g of x the following. G of x, if I have, so cosine Cosine here goes to sine. Make my little table. And I wind up here with sine. Now I'm going to make a guess. I'm going to guess that this is 2x. But then when I take g prime of x, I wind up with 2 sine, cosine. Right? If I take g prime of x here, I'd wind up with cosine of 2x times the derivative of 2x, which is 2. So I need a 1/2 in front to get rid of the 2. How do we feel about that? That just idea that what I did was I took the derivative of the thing I was trying to figure out, and by doing that, I was able to figure out that there should be a 1/2 in front. Right? It's an idea. The idea is that I'm just playing with it a little bit. Okay. So by doing that, I wind up with the following. I wind up with this being the thing that goes on top. So I wind up with the limit as x goes to 0 of this thing, 0 to x, cosine 2t dt over x equals the limit as x goes to 0 of 1/2 sine of 2x minus 1/2 sine of 0, 2 times 0, over x. And of course, this term right here is just 0. All right, so how do we feel about that, 1 to 5? That was a very tricky antiderivative if you did it this way. Okay, and then you can either use L'Hopital's rule on that, that's legal, or you can, oh, this is just sine of u over u as u goes to 0, that's 1. So either way there works. Okay. This problem is hard. It's harder than the ones on the test. The reason why it's hard is because there's really 2 steps involved. You have to realize that you can use L'Hopital's rule on this top bit, and then you have to do the derivative correctly using FTC1. So that's kind of a 2-stepper. If these things show up on the test, what'll show up is either, it's either a L'Hopital's rule problem or a problem where you need FTC2. I think using both makes this one very hard. And then this antiderivative is also kind of hard. So why did I substitute u? Because I wanted to use the special limit. I could have also, right, if I want to use the special limit, I got to put it in this form. So this is the 2x right here on the bottom. There's a 2x right there. Make that u, then u goes to 0. Or I could have applied L'Hopital's rule to that. One round of L'Hopital's rule would have done it. So, any other questions? Okay. Again, this one was hard. go to the next one here. So the next one is another one of these, except the properties all look weird, right? And it's actually not that. The conditions themselves are disguised. This is a problem with a lot of bark. It looks bad, right? It's a problem with a lot of bark. Let's just do it. So what does this first condition say? I'll leave that as an open question for a moment and come back to it. So if someone wants to say that in chat, that'd be great. The second condition. The limit as x goes to infinity equals 0. Okay, I'm going to do that right there. I'm going to put a little guidelines here. So what I did was I just added my little limit, and then I put a little horizontal asymptote on that side. F is concave up on -2 to 0. F of 0 equals 0. The integral from -3 to 0 of f of x dx is less than 1. The limit as I go to -infinity equals 1. F prime is greater than, f prime of x is greater than 0 on -1, 1. Now, this is another one of those tricky conditions. What does this one say? So our questions were, what does that one say? And someone answered that one. This means it's continuous. What does this next one say? I'll leave that open in chat. Oh, it's already done. Yes, that's right. F prime of 1 does not exist. And I know it has to be continuous. There's only one way to do that. Kink. Okay, f double prime of x equals 0. That means we want an IP right here. So that means that this area right here needs to be concave down. And then there's this condition. This last condition. This says I need to acquire from 1 to 3. I need to acquire 2 areas. So this means that the derivative from 1, the integral from 1 to 3, the area under the curve of f of t dt needs to be greater than 2. And then it says that the integral from 3 to x of f of t dt needs to be greater than 0. So what this means is that I need to acquire 2 area from 1 to 3, and then I need to never acquire more negative area. Right? I need to never lose. I need to accumulate 2 area and then never lose it. Now, how do we feel about what all the conditions, 1 to 5, how do we feel about every condition except the last one? What these conditions mean? Right? They look intimidating, but they do look intimidating. Right? But you have to translate them. So every condition but the last one. Okay. Well, let's see if we can do this sucker. I've got some concave upness here. So from here, I can do anything as long as it's continuous. Let's look at our notes. Okay, in this area here, I can do anything as long as it's continuous. This one has a bunch of conditions happening at once. So I'm going to deal with that now. Do you see how this area right here, there's a whole ton of crap happening? I need to be ascending, I need an inflection point, and I need to be concave up. So there's a lot of crap happening right here. So let's deal with that. Let's make this thing look a little bit like this. Okay. All right, so that deals with that bit. Let's redo the tail here. Let's come down a little and kind of come up like this. All right, I'm just reading the directions on the bottom here and looking at what that would mean. Okay. Oops. All right, how do we feel about that? I'm just looking at the conditions and saying, what would that mean? Okay. Well, let's see. We got concave app action here. We need negative area. That's fine. I've got it. And then I just need this to kind of go off that way. 1 to 5, how do we feel about translating the left-hand side with like 3 conditions at the same time on this side? 1 to 5, how do we feel about that? This is a lot of conditions at the exact same time. All right, please keep asking questions in chat. Now on this side, I'm going to come up here. I need concave down, but I need increasing. So I'm going to keep increasing, but stay concave down. And then I'm going to kink. Now, what do we feel? Do we feel we should kink up or we should kink down? Right? Because I need the derivative not to exist. Well, let's see. I want to accumulate positive areas, so let's kink up. Let's do it. Card kink up. Okay. So I do a hard kink up. Now, there's nothing here saying that I need this to be smooth, right? There's no derivative condition. So let's just keep the ruler out. Now, there is a condition that says that I have to go down this way, right? I have to go towards 0 on this side. So let's make that happen. Oops. Let's make that happen here. Let's just head on over to 0. Oh, we got a little vertical line test violation going on over there. Let's just go on down to 0. Something like that. All right. Now I need to accumulate positive area. I need 2 accumulated areas, and then after that, I don't care as long as it's positive. As long as I never lose area, who cares? So let's accumulate some area. Well, there's nothing that says that it can't be kinky here too. It doesn't have to be. But, you know, straight lines are easy to draw when we have a little ruler or our student ID. And I get something that looks like this. All right. All right, and now let's check it. Is it the case that f of t equals, is it the case that I'm continuous everywhere? Yes. Is it the case that I went to 0? Yes. Make a little asymptote there. A couple more lines. Is it true that f is concave up from -2 to 0? Yes. Is it true that f of 0 equals 0? Yes. Is it true that the area under the curve from -3 to 0 is less than 1? Well, 1 is positive and it's negative, so yeah. It's not only less than 1, it's less than 0. So I have met that condition. It's all negative area. Is it the case that as I went to negative infinity, that's true? Is it true that f prime is greater than 0 on -1, 1? Am I going up? Yes. This is a little ambiguous. Let's make that just a little bit harder. Okay, just so they can't accuse us of not doing it right. Is it the truth that f prime of 1 does not exist? All right, that's f of 1, right? Kink there. I will even label it for the greater. Okay. Is it the case that f double prime of 0 equals 0? Yes, and I will even label it for the greater. Is it the case that I've accumulated is it the case that the area from 1 to x is greater than 2 for all x greater than 3? All right, so my base point was 1. All right, so this was the base point. And then I just continue on positive. And so I have this idea that I accumulate area as I go along. So that one's fine. Check, check, and check. How do we feel about that 1 to 5? Could you have made it a flat line, as in actual flat? You mean like kinked it here and just had it go straight? Yes. If that's your question. Could you have made it a flat line at x equals 1? As long as you got high enough to accumulate 2 area, yes. But then you had to come back down to limit to 0. The derivative doesn't exist. Yes, yes. No, at x equals 1, you needed a kink. The derivative did not exist. I'd have to look. So people are asking about that, and I'd have to look at it. So how do we feel about this sucker 1 to 5? There's the final poll there. This is a hard one. We got multiple polls going on for the 1 to 5. Okay. All right. So that's about, now this last condition here does not show up on the test. Even I'm not that mean. This type of condition can definitely show up on the test. This one's too hard. This was too, it's not that it's too hard. I have expectations that you guys would be able to do it, but it would make people cry blood tears in other sections, that weren't you wonderful people. So it would never get out of it would never be allowed. But this one's fair game. This one's a good one. Actually, they're both good, but Any other questions? Okay. So let's move on to the day. Last time, I didn't do an outline, did I? Horrible me. So last time, we did prove FTC. Today, we're going to talk about initial value problems. And there is a typo on the homework that I just found. So I will deal with that, now. And I'll say that it's if you did the old homework one, there's a typo. It's supposed to be decreasing, and it's not, because I put the dot in the wrong direction. So I'll get to that in a minute. Okay, so these were part of section 4.7. And it looks like this, right? These were part of section 4.7. So how am I going to approach this problem? Well, the point is that there's two ways to do it. All right, and one of the ways is better. Okay, it's the first point is what? So I know that f of 1 equals 4, and I know that f prime of x equals x squared. Okay, so the antiderivative of this, the first way I'm going to do it, so the first way to do it is simply to take the antiderivative of f prime and solve for c. All right, so that looks like this. All right, how do we feel about that 1 to 5? What that antiderivative is? Someone has asked, what do I recommend for the better study material? I think the better study material, the bootleg is way harder because it's meant for an in-person final with proofs on it. I'll talk about that later, but the proofs have been cut. So what's left is it's not that they've been cut. It's that there's no regurgitate the proof problem. It's been modified to just be true false questions. And because of that, the both of the practice exam and the bootleg have too many proofs on it because they're really true false questions. The best study tools are the old quizzes. So if you want the absolute best study tool, okay, it's to take that problem sheet that I gave you. On it, I listed all of the quiz questions, even from the rest of the class, that you should go review. So if you're pressed for time, your biggest marginal impact, oh, look, the margin, your benefit at the margin, your derivative is highest for the quiz problems that I put, the quiz questions that I listed on the practice test. I'm sorry, not the practice test, the review guide. Okay, does that answer your question? Okay, back to this. So how do we feel about this method here? All right, so I took the antiderivative, and now I'm going to solve for C. So what I'm going to do is I say, okay, well, f of 1 equals 1/3 times 1 cubed plus C. And that equals 4. All right, f of 1 equals 4. F of 1 is 1/3 1 cubed. Well, this means here that 1/3 plus C equals 4. So I subtract 1/3 from both sides, and I wind up with C equals 4 minus 1/3, which is the same thing as what? 3 2/3, right? Yes? No one's going to say? That's 11/3, right? Okay. How do we feel about that method 1 to 5? So I get that f, therefore, f of x equaled 1/3 x cubed plus 11/3. Okay, so that's one way to do it. There's a better way to do it. All right. So what does FTC2 say? All right. It says that that the integral from a to x of f of x, f of t dt, not f of x, equals g of x minus g of a. Now, here, what I have then is that the integral, let's rewrite this in terms of this. That means that f of x minus f of a equals the integral from a to x of f prime of x, I'm sorry, f prime of t dt. How do we feel about that, 1 to 5? Right, all I did, this is the thing, this is the statement here. Right, so there's my statement. And what I did was I just restated it here, right? f prime is this f here, right? Because what I've got here is f of a equals, right? So the derivative of f is f prime of t dt. Okay. Well, I changed it to t because I have an x up here. Right? So I don't want to be ambiguous. It's a good question. All right. Well, let's look at my information. My a here I have is 1. I know that f of 1 equals 4. So now I'm going to rewrite this as the following. F of x minus f of 1 equals the integral from 1 to x of f prime dt. Well, that was x squared, so that was t squared dt. And by the way, I'll explain what I mean by when I say that this is a better way to think about it. Okay? That does not mean that it's the way that you should do it on the test. It means that in real life, when you need this skill, this is better. And I'll tell you why in a minute. Okay, well, let's do this. And that's really the same piece of it, right? This g of x, when I do this, which is f, is going to equal what? Well, that's going to equal 1/3 x cubed. I don't need the general antiderivative. I just want an antiderivative. So that implies that f of x minus f of 1 here was 4. Equals the antiderivative equals 1/3 x cubed minus 1/3 1 cubed. Okay. Well, that means that f of x, if I solve for f of x, I get 1/3 x cubed minus 1/3 plus 4, which is the same thing as 1/3 x cubed plus 11 over 3. How do we feel about that 1 to 5? Okay. Now, if all we were concerned about in life was the test, if I didn't care about anything but the test, I would not show you this. Because this right here for the test is usually a faster, easier method to getting everything done. Okay? This is a much more sophisticated approach. All right. So if all you're interested in is maximizing your points on the test, this is better. But if you're not interested in that, if you're interested in more, okay? If you're interested, if you're interested in something more sophisticated, all right, this approach here will give you better results in real life. And I'll tell you why. There are a lot of these functions, okay, that don't have nice, pretty antiderivatives. Okay? Or when they do, that they're either you can't find them, or when you do find them, they're absolutely horrible. Okay? And a good example of that is the normal distribution, right? It's its curve looks like this. Its antiderivative looks horrible. So this is the probability distribution function. And if what I want is the cumulative distribution, right? When I take the probability distribution function for this sucker. Oh, I'm showing you the wrong screen. So this right here is a normal distribution. This is the curve for it. This is straight off Wikipedia. Okay? And the curve looks like this, and that is ugly. All right, are we all on board? 1 to 5. How do we feel about the fact that this is an ugly curve? Right here. That is going to be a very nasty function. Okay? And what I want is the area under the curve. Right? Because what I want to know is what percentage of the population is between two z-scores, right? I want to know when I'm looking at this thing, I want to know, okay, what percentage of the population is from here to here? Okay, so when I take this integral here, what I want is I want to consider the normal distribution, the integral, what percent of the population, or what part of the population is between A and B. Right? I want to know what part of the population is here to here. And that means what I want to do is I want to take an integral. What I want to measure is the area under the curve from A to B. How do we feel about what we want to do? Why this is important? Okay. 1 to 5. How do we feel about this application of integrals? All right, you may have seen it before, this area under the curve thing. And if you flip to the back of your stats textbook, you're going to see a big table with a whole bunch of numbers, right? With all these z-score things, and et cetera, et cetera. But what you're actually asking is the integral. What you're asking actually is the integral from a to b of f of t dt. All right, is everyone on board with that? That's this application here. That's what we care about. And this integral is ugly, especially if I have weird constants. Okay? But remember that midpoint stuff that the book went over? I can actually remember the integral is nothing but a limit of Riemann sums. So I can estimate it by using Riemann sums. So suppose I have the following question. So if I want to say I'm building like a, suppose I'm doing something like I'm building a, let me put it back on scene. Let me see here. Right? So suppose, here's an example. Suppose I'm designing an office chair, okay? And I want the chair to accommodate people that are 5 feet tall, and then accommodate 45% of the population. Okay, that is, from 5 feet tall. How can I accommodate 45% of the population? In other words, I want to know how tall, how much, at what should be the upper cap. But I can get good estimates, right? So what's the problem I'm solving? So let's do that. If A equals 5 feet, what B do I need to capture 45% of the population? In other words, I want to do this problem. Right? I want to go from 5 to whatever. Equals 45% of the population. And I might not be able to get a good estimate on this. Does that make sense? And I may want to solve for other things. I may want to solve for this in general. Okay? Where my base point is. So if I use FTC2, if I use this method, I can then get something I can approximate. And if you have one of these scientific calculators that we banned on the tests for this reason, your scientific calculator will actually do the calculation for you and give you a numerical answer to this problem. So how do we feel about that, 1 to 5? 1 to 5, the reason why we care. Okay, let's do one more. All right, so let's do this problem, except let's do it right because I messed it up. So let's see here. Are there any questions, by the way, while I'm doing this? This would be a good time to pause and ask questions. So there is the typo. Because it's open. All right, so let's do another one now that I fixed the typo. Here's one from the problem set. All right. In economics, the total cost curve, better yet, let me just do this. And I will fix the thing online. If you did it with the other one, that's fine. I won't penalize you for that if you've already done it. How do I take a picture? There it is. All right, so let's do another example here. Excuse me, everything is now disorganized because I found that. Yes, so the question is, do I still have to take the antiderivative for both? Maybe, right? If I'm doing the method 2, and this is why I said it wasn't the best approach for the exam, but why it's a better approach for real life, is what if I can't take an antiderivative? What if the antiderivative is not clean? I can still do a numerical estimate. Okay? And let's come to this example here. Okay? I have a marginal cost curve, and what I want to find is the total cost curve. Okay? Well, if this is my marginal cost curve, if my marginal cost curve is 200 times q plus 1, what is the marginal cost of the first unit? So if I plug 1 in for q, what's going to happen? Why does it do that? Why does it? Oh, I know why it does that, because it's in full screen mode. So here's the curve, 200 times x minus 9. And so what's the cost of the first unit? The marginal cost. Well, the marginal cost of that first unit is 63.246. Okay? So m of 1 equals 63.246. All right? So the total cost to produce one unit is what? It's the marginal cost of the unit plus my fixed cost. So my fixed cost was 2,000. All right, how do we feel about that? 1 to 5. All right. I think I've lost people. When I said this is not the best way to go about it for the test, I think like half the people went and, oh, bye bye. I think like half the people went, no. All right. Now, what's the marginal cost of that second unit? Well, the second unit is what I get when q equals 2. And that marginal cost is 60.302. And then, so what's the total cost of producing 2 units? Well, it's the cost, the fixed cost, plus the marginal cost of the first unit, plus the marginal cost of the second unit. So it's 2,000 plus 63.246 plus 60.302. So what I'm doing here let's make this a little bigger. And then if I wanted to compute the cost of 5 units, what would I do? Yeah, let's just stick to this. Let's stick to the units we have. So let's take a picture. So what have I done here? All right, I've taken the marginal. What I'm doing is I'm adding the fixed cost plus this. All right, so the cost of producing that first unit is 1 times 63. Okay? The cost of producing that second unit was this one plus our total cost. How do we feel about that? 1 to 5. Okay. Well, is there anything special about selling gasoline by the gallon? I mean, besides the fact that it's dirt cheap now. I swear, I went up to Wawa the other day and they gave me a free tank of gas with the purchase of a hot dog. Okay, I mean, that's how cheap gas is right now, you know? You go buy the car wash, they give you the gasoline. All right? But there's nothing particularly special about selling it by the gallon. What if I sold it by the half gallon? So here's my question. What is the cost of producing what is the cost if I measure by the half gallon? Well, there's the marginal cost of producing the first half gallon. Right? And I have to multiply it by 0.5 because I'm only doing the half gallon. So, what is the marginal cost of producing that first half gallon? Where'd Desmos go? Give me back Desmos. Well, the marginal cost of producing half a gallon is 64 point, by the half gallon, is 64.909, sorry, 64.889 times 1/2, because the marginal cost is in per gallon, and now I'm doing per half gallon. right? So the marginal cost of producing half a gallon of gasoline is, for the first half gallon, is 64.889 times 1/2. And then the marginal cost of producing that second half gallon is there. The marginal cost of producing that third half gallon, the marginal cost of producing the fourth half gallon. Whatever that is. 61.721. How do we feel about that, 1 to 5? Okay, so where is this going? What am I doing here? I'm doing a Riemann sum. Is everyone on board with that? So it turns out that my total cost right, is going to be the total cost is the fixed cost plus the integral from 0 to q of the marginal cost. The cost curve was 200, and I need to switch to x. I need to switch my variable. Right? Which would have given me the exact same answer if I had done, and then, right? And this right here is the total cost of 0. And then that corresponds to the fundamental theorem of calculus, course TC of Q minus TC of 0 equals 0 to Q m of x dx. How do we feel about that? 1 to 5. So there's two. Oh, I got to do the 5 pole, don't I? I'm sorry, I'm over. But, it's the last class. Well, I feel. All right. Okay. So that's kind of the end of the course. It's just this last bit on practical applications of the integral. The one on the exam is nowhere near as complicated, and you can do it in 2 different ways. If you want one that's similar to the one on the exam, the bootleg's a nice one to go with. That bootleg question's good. Also, the question that's on the practice exam is very good. The bootleg one's actually harder than the one on the exam. But the whole moral of the story is that you can do these in multiple ways. Now, for peer leading is optional. I'll make an announcement about that. What's going to happen is that everyone, I think the way it's working is that everyone from my class is going to meet at 11 o'clock. And we're not going to have a 9:30, but you will be in your groups. And you will be working on the practice exam. There'll be peer leaders there. I may pop my head in. I'm going to have extended office hours on Friday. I may even do another session on Friday, depending on what the demand is. Okay, so let me just wrap it up. Today we talked about initial value problems, that there's two ways of doing them. There's taking the antiderivative and solving for C, and there's using the fundamental theorem of calculus part 2. For the test, this is probably your best bet if what you're trying to do is optimize your grade. However, in real life, using this method here is probably better because you can get estimates very quickly, because you can do algorithms. You can write computer programs that'll do these for you, that'll give you numerical estimates for these things. And if what you're interested in is numbers, you know, because you're doing chemistry or medicine or something like that, which is chemistry, then using the FTC method is better. And all those tables that you see in the back of your stats books, the tables that you see, the approximations that you see in your medical textbooks for various AUC functions, all of that comes from this method here. All right. Thank you very much. It's been a wonderful semester. I'm sorry it ended like it did without us being in person. If you had a good time, if you learned something, if you felt I did a good job, please go on Rate My Professor. Give me a rating. It helps me recruit students for next semester. My name was Scott Grizzard. If you didn't have a good time, I'm sorry about that. If you didn't feel like I did a good job, I'm sorry to hear that. Please go on Rate My Professor and give me a rating. My name was Robert Connolly. And I will see you. I love you guys. I'm sorry I missed you. I'm sorry we ended this way. Please don't be a stranger next semester. Come by and see me. I'm not teaching Calc 2, but there are several good people that are teaching Calc 2. And if you want to talk about anything at all, stop by my office and I'll be happy to talk with you. That's it for me. Bye-bye.